This year for Retic Fest 2025, we actually had Clint Laidlaw of Clint's Reptiles come out and break down the science on Super Dwarfs. You're gonna wanna lube your brain up for this one. No, that's not the right saying. What do you say when your mind's about to be blown? Whatever that is, do that now. This video is gonna get wild.
These are the big questions about little pythons. Are super dwarfs an example of insular dwarfism? This is not an elephant, but it is a proboscoidean, so it's super closely related to modern elephants, and it's like this tall. That has happened in this group many, many times, multiple times, just on the island of Flores. The island of Flores is actually very close to the Solera archipelago, where the Super Dwarf Reticulated Pythons come from. There's also a whole species of humans from the island of Flores. They're called that. They're also called hobbits, because they're tiny little people. There's something called insular dwarfism, where organisms tend to get small on islands. There's also something called insular gigantism, where organisms tend to get huge on islands. You know, if you think about the largest tortoises in the world, where are they found? Islands. And they're not the largest by a little. They're way bigger than the next largest tortoises on Earth. Sometimes animals get huge on islands, and sometimes they get tiny on islands. The big problem is there's actually not a heck of a lot of food on islands. You've got what are called trophic levels. Okay, so your lowest level trophic level is, you know, the primary producers that are making all of the sugar, and you know, these are largely plants on an island. Other things can eat them. Only about 10% of the biomass moves from one trophic level to the next. So primary consumers, things that eat plants, there can only be about 1/10 the biomass of those that there can be of plants. And then it go up another level to the secondary consumers, the things that eat the plants. Only about 10% of that. You can't have a lot of carnivores. Certainly not a big population of T-Rexes on that same island, right? Like that's not going to work out. You could probably have some full-size, say, African or Asian elephants on an island for a while, right? Like you have a small island, it might be able to sustain a dozen elephants. The problem with a dozen elephants is it's really easy for a dozen elephants to go extinct. If for no other reason, then like the probability that at some generation all of them will be male, fairly high, actually. The likelihood of flipping 12 quarters and having them all be heads sometime, pretty darn high. It's just really easy for 12 animals to go extinct. So because there are no large herbivores on these islands, that actually opens the door for things that don't use nearly as much energy to get big, like say tortoises, to get huge because they don't have to compete with large predators. That was also given to me as the whole explanation for insular dwarfism, why they're smaller on islands, which would be a great explanation, in my opinion, for why elephants can't colonize islands. But that's not what we see. What we see very clearly in the fossil record with all of these groups is big elephants colonize islands, and over multiple generations, big elephants become small elephants. Something that evolution doesn't do is it doesn't think ahead and go, gosh, guys, we are a small population. Our likelihood of extinction is through the roof. We gotta get little, fast. There has to be something now that drives them getting smaller. You know, in the time before they would have gone extinct, that was making them smaller, and that's why the ones that persist long-term are the ones that actually got smaller, but why would they get smaller over time? Early in life, everything is investing in two of these things: growth and maintenance of the soma, maintenance of their body unrelated to reproduction. Usually, at a very young age, not very much in reproduction. That's the third place where you might put your energy. At some point, you either stop investing in growth or you greatly reduce your investment in growth. And you can do that sooner or later. If you do it later, there's a big benefit. You get bigger, which means you can either have bigger babies or you can have more of them. And the trade-off to getting really big is it takes a while. And it takes a lot of energy. And if you can't find that energy, or if you're likely to get killed by something, well, you end up dying without passing on your genes for, hey, let's wait a while before we stop investing in growth and start investing in reproduction. And all those individuals that started a lot sooner are the ones that actually pass on their genes to the next generation. So when it comes to what genes are present in the future, it's the ones that managed to get themselves reproduced in the past. If it takes a lot less energy to get large enough where you start breeding, well, hey, your genes make it. And it was coded in your genes to do that, to start reproducing younger. The ones that had it coded in their genes to wait longer didn't pass their genes on. And generation after generation after generation, this continues to be true, and you're not paying the cost of not getting big because there's no large predators on small islands. The smaller its genetics are, the more likely it is that it's going to be able to find enough to stay alive and reproduce. What is parthenogenesis, and why is it common on islands? Parthenogenesis just means that they're reproducing asexually. Okay, these are members of groups that are normally sexually reproducing, and they're reproducing asexually. There's a few different ways this can happen, but the way that it happens in these two is a little bit different, because this one on the left is a mourning gecko. They practice obligate parthenogenesis, which means that's the only way they can make more geckos. They are producing full clones of themselves. Whereas the Komodo dragon there only produces a half a clone. A female Komodo dragon will lay unfertilized eggs, some, but usually not all, for reasons that'll make a lot of sense here in a moment, will hatch, and all of the babies are males. That's a little odd, right? It's pretty cool. Now this is my first retic when she was a little younger. She's also a result of parthenogenesis. She is a female though, as were all of her siblings. Because when reticulated pythons do parthenogenesis and produce a half clone, they make only females. And when Komodo dragons do it, they make only males. There's a reason for this, and it's the exact same reason. So what a half clone is, when you, as a diploid species, which means you've got 2 of every chromosome type that you've got. You got 1 from mom, 1 from dad. So for every chromosome type that you have, all 23, you got 1 from mom, 1 from dad, 46 total. When you reproduce, you don't pass on all 46 of yours, or else your offspring would have 92. So you can't pass on all of your chromosomes to all of your offspring and then mix them with somebody else who's also giving all of their chromosomes. So you got to cut them in half, and you split it right down the middle. You give either moms or dads for each one, and it's not like moms all lined up on one side and dads on the other. Then there would only, like your parents could have only had 4 possible types of children. That's not the way that works. Instead, it's this one and this one. They ran. I don't know which one's from mom, which one's from dad, but you get a random one there. You get this one, let's say, and it goes down. Each one of your parents can make 23 factorial different types of gametes, which is rather a lot. The reality is your parents could make so many different kinds of kids that, excluding identical twins, which started with just one zygote, if they were the parents of everyone on Earth, there would probably be no duplicates. That's the way that works. Not the case for my girl, though. In this case, they gave the half to the egg, and then they went, all right, sperm. All right, sperm is not coming. Usually, that just means, well, I guess I'm not reproducing. Sometimes, though, you get an oddball who's like, let's just copy these chromosomes and go with it. And so they make identical copies of everything. These 2 animals here are homozygous for everything. They have no hets. They are as inbred as it is possible to be. Okay? That's the whole thing with inbreeding, by the way. Inbreeding doesn't cause mutations. It's just virtually everybody has some recessive alleles in their genome somewhere. That would be just horrifying if they were expressed. And everybody's got them. Everybody's got them. The good news is the one that you got from your other parent, totally different, totally covering for it. It's doing what it needs to do. And all is well. And the likelihood of you finding somebody else who has those same exact horrifying recessive alleles that you do, super low, unless you're closely related to each other, especially if your family's been doing this for a while. Okay? All of a sudden then, the likelihood of homozygosity goes way up. Well, in this case, they're just homozygous for all the things, everything, all homozygous. A good part of the reason why that was my first super dwarf from Garrett is because A, he knew I would love that, and B, he felt bad selling it to anybody because it could just drop dead at any moment. Who knows what's wrong with this genome? And it's fairly likely something catastrophic is wrong with it somewhere, and that will crop up at some point. I would estimate when you get a parthenogenic clutch, even from retics, that a larger percentage of the eggs probably don't hatch, and much more fail to thrive early on. It's even worse for the Komodo dragons. Reticulated pythons are XY like we are, which means that the females have 2 X chromosomes. So for each of these half clones, they're either passing on this X and it's duplicating itself, making a female, or they pass on this X and it duplicates itself and makes a female. That works. They're massively inbred, but other than that, works great. For this guy, well, girl, all right, they're what most snakes are. They are ZW. ZW is exactly the same as XY, except it is the females that have 2 different chromosomes. They're what you call the heterogametic sex. They can make 2 different kinds of gametes. Males are ZZ. So if males are the one doing the parthenogenesis, it would be the same, but males are horrible at doing parthenogenesis. The females, though, they can pass on one of their Z, because they got a Z, and if they do that, it's a ZZ male. They pass on the W, WW dead, just as dead as you'd be as if you were YY. Too much stuff missing there. They only produce ZZ males. Both of these things are awesome if you live on an island. For one thing, probably doesn't come up too often if you live on the mainland. You might be able to do parthenogenesis, who knows? But the likelihood that no sperm is going to come when you're like, I would like some sperm, like it's coming. There's going to be sperm here. Like, you're like, do I not make any pheromones at all? Oh, here they are. You would never even know if you could do parthenogenesis or not. It just doesn't matter. I don't know if you remember that scene in Castaway when his son was born. Me either, because that never happened, right? He was all by himself on that island. And generally speaking, that's what happens to animals that get washed up on islands. It's like, whoa! Well, I'm glad I'm on something. I hated being out to sea. Are there any mates here? No, there are no mates there. Unless they happen to wash up like gravid, they live out their lives and they die. If it's a reticulated python, most of the time that reticulated pythons have washed up on random islands, they have probably lived out their lives and died. Every now and then, maybe you've lucked out and had one that was gravid wash up. But what has happened every now and then is one of these oddballs that can do parthenogenesis washes up. And instead of just living out its life and dying, it produces all of its hyper-inbred babies. And 700 years later, when a male washes up for the first time, he arrives in the land of the Amazons. And they are all descendants of females that can do parthenogenesis. You've selected directly for can do parthenogenesis. Bam! Now you've got a brand new sexually reproducing population. The likelihood of establishing a population there is so much higher, because the two snakes don't have to wash up simultaneously. Off they go at that point. Komodo dragons, kind of even funnier. The female only produces males. Half the eggs die because they're WW. A lot more are going to die before they ever hit maturity because they're stupendously inbred. And the ones that make it to maturity, there is nothing wrong with that genome at all. There are no nasty recessives hidden in there anywhere. They're all dead. You have created for yourself the best possible inbred mate. There is like zero chance you're going to have any problems with their direct offspring. You've given a huge bottleneck to all the nasty recessives in your genome. It's a really good system. Both of them hugely relevant for establishing populations on islands. Parthenogenesis is just a neutral ability on the mainland. On an island, in many cases, it's everything. Why can't you make a 98% super dwarf morph? Reticulated pythons, I looked it up, they have 36 chromosomes. So they get 18 from each parent. If I took a super dwarf and I wanted to breed in a new morph, or if I just wanted to breed it to a mainland reticulated python, because people do that, I want to have the highest percentage super dwarf I can get. I take the offspring that I produce from that, which will be exactly 50% super dwarf. I breed them to a 100% super dwarf. And now I've got, on average, they're going to be about 75% super dwarf chromosomes. I breed them again. I take a 75% super dwarf, I breed it again to a 100% super dwarf, and now I get on average 87.5% super dwarf. The reality is it can actually be anywhere between 75 and 100%, but on average, 87.5. I do it again. I breed that 87.5% super dwarf to a 100% super dwarf. I now get on average 93.75% super dwarf. I do it again. 93.75. I breed that. I get on average 96.875% super dwarf. I breed it again. Breed that one to 100. Now I got a 98.4375% super dwarf after 6 generations. I have made a 98% super dwarf. Give me a morph, tell me how it's inherited. Tiger. Tiger's incomplete dominant, right? That first one's a tiger. Well, why the heck can't I just do this with the tiger and have it be at the end a 98.4375% tiger super dwarf? When I did this, I was being random. I was just breeding for percent super dwarf. That's all I cared about. And I can't see it, so I'm just guessing. But when I save the tiger, every single generation, I'm saving at least one mainland chromosome. They've got 36 chromosomes, which means that every single chromosome is 2.8% of their genome. Which means if I got rid of every single mainland chromosome in that genome, except for the one that has tiger on it, it's still only a 97.2% super dwarf. I could breed it for 1,000 generations. The more morphs that you're layering on there, if they're occurring on different chromosomes, say you've got albino and something else that's recessive, albino pied. I've never bred my retics. I just like them. If I save 4 chromosomes, that's 10% of the genome right there. Guaranteed. You can do that math that we did before on the rest, but you've got to do it just simply on the rest. But that first 10 is guaranteed to still be mainland because I saved it on purpose. Here's the last thing. Are superdwarfs a species? I've heard this is not a controversial topic. And the good news is I don't breed superdwarfs. So if everybody in the superdwarf community is mad at me, what do I care? Okay. So, because I don't even know what you guys want to hear as far as this goes, because both have ramifications. Right now, if superdwarfs are considered to be reticulated pythons, well, there's all kinds of regulations on moving reticulated pythons around in states that won't have them because of their size, because they get too big. That's, generally speaking, that's the problem with them. Superdwarfs would be amazing, right? They probably wouldn't have those same regulations on superdwarfs that they have on mainland retics if they were considered a different species. But also, if they're considered to be different species, they may suddenly become endangered. And now you've got all sorts of new regulations on them. So I don't know what you want to hear. But that won't keep us from figuring out what is true. Okay, and so I got a horrible question for you. What's a species? A lot of people think it's an easy question. And it is, as long as you stop thinking about it immediately after you define it. If you just like polled 100 Americans, 7 of them would give you an answer, and that answer would probably be, if you've got 2 individuals that can reproduce and produce offspring that can reproduce, they're the same species. That's effectively the biological species concept, and there's nothing wrong with it. The main problem with the biological species concept is it's really hard to apply. Like if I find 2 T-Rex skeletons, could they have ever reproduced together? I don't know. I could find them mating. I wouldn't know. Say I got a population of tortoises that's lousy at crossing rivers, and a big, an earthquake happens and it diverts a river and cuts the population in 2. Are they 2 species or 1 species? Superdwarfs that you've got here in the United States, are they likely to ever breed with any of them that are currently existing in the Solera archipelago? No, they are not. Right? So are they a different species? It's really difficult to apply. This is the evolutionary species concept. The species is a single lineage of ancestor-descendant populations which maintain its identity from other such lineages and which has its own evolutionary tendencies and historical fate. It basically means they're different, they're significantly different from other populations in some measurable way, and they're not really having much gene flow, if any. These guys are establishing a colony on Mars. If they go, say 300 people go, the moment they land there, their gene pool is going to be dramatically different than the gene pool of Earth, just because of founder effect. Now they're under a very different selective regime, and they live for the next 200 years. Are they different? Heck yeah, they're different. However, if 300 years from now, it gets a lot easier to go back and forth to Mars, we're sending people there all the time, they're coming back here, there's all kinds of Martian Earthling families going on. Are they a different species? I wouldn't say so at all. I don't think anybody would. Right? That's the same species. They had a few 100 years where they went off in a separate direction for a while, and then they came right back in. However, if they just stay on Mars, right? They're like, we hate Earth people, right? And they just start shooting down any Earth ship that comes, and they're like, we're never going to Earth. As long as that continues indefinitely, like they're, yeah. So the question isn't really could that result in a new species? It's when am I going to call it? How long do they need to be off on their own, doing their own thing, before I go, I don't think they're ever coming back together. I think for the most part, superdwarfs absolutely fit this description. The main thing is just, do we know that they're going to keep on going in these different trajectories? And I would say we probably do have good reason to suspect that there's not going to be a huge amount of gene flow. Not that none will happen, but I would say you could make a very strong case for, yes, they're on their own, and no, they're not coming back. So if you want them to be a different species, there is definitely a place for you to start making an argument, and then it would probably come down to just quantifying, like, how different do they have to be? There's a little bit of research that has been done, which is why they're currently considered, I think, 3 total subspecies. Not very much. Finding that out might not be in your interest, I don't know. That has covered the questions of, are superdwarfs an example of insular dwarfism? Yes, they are. What's parthenogenesis and why isn't it more common on islands? I think we covered that. It makes it much easier to colonize islands. Why can't you make a 99% of any mainland morph superdwarf? And are superdwarfs their own species? I don't know, but it's certainly a possibility. Do you have any questions?
Do you have any questions? Comment below. It make great content for future videos, so go ahead and subscribe at the same time. Thanks, guys. Catch you next time.